while inviting our today's first keynote speaker. He is Professor Dr. D.K. Mohanta. He received his engineering electrical from College of Engineering and Technology, Bhubaneswar, India. He received his ME from IIT Mesra and PhD engineering from Jadavpur University, Kolkata. He is having tons of experience in industry as well as in teaching and research. He has published in very renowned publications such as IEEE Transitions, IET, Elsevier and Taylor and Francis. He has also patented his work. He is currently working as professor at IIT Mesra, Ranchi, in the Department of Electrical and Electronics Engineering. He is also currently editor of Electric. He is currently the editor of Electric Power Components and Systems Journal, Taylor and Francis, associate editor of IEEE Access, and subject editor IET Generation Transmission and Distribution. He is also the guest editor-in-chief of special issues in IET Generation Transmission Distribution in Emerging Trends in Systems Integrity Protection Schemes. With this, I want to request Professor D.K. Mohanta sir to please, can we record this session?
Yes, yes.
From
yes,
the
you can
permission?
record. Yes, yes.
Okay.
You're welcome.
Thank you, sir. With this, I want to invite Professor D.K. Mohanta to deliver his talk on the topic of an overview of microgrid reliability. Thank you, sir.
Okay, good morning to all. Very warm welcome for this course on so this is my outline of presentation. First of all, I'll explain what do you mean by electric grid, then how the microgrid is having similarity and dissimilarity with the electric grid and conventional grid, and then we'll go for the microgrid reliability. For that, I'll speak about some basics of reliability, then accordingly we'll go forward. So here electric grid, basically, why we say grid? The meaning of grid is interconnection. So this electric grid or power grid interconnects the generation to the transmission to the distribution system or unit. So that power can be sent from the generating unit to the load through a particular type of interconnection. That's why it's called electric grid. American National Academy of Engineering says that the most complex engineering marvel of this century is electrical power grid. So it supplies electrical power from generating unit to distribution unit, and it's a bulk power. So it is a typical diagrammatic representation of electrical grid, where you see here is the generation station, and here lines will be transmitting, and here distribution substations, they will be giving to the different whole houses, loads, or industries. So this is our microgrid then. So basically grid is nothing but interconnection from transmission to distribution. And if you see, this is the scenario now that national grid means all the regions of India have been connected. From here, 5 regional grids post August 2006. We have again future 2014 onwards also one grid, one. So much of interconnection is there in a conventional grid. That's the point. Grid means interconnection. Now, what is a microgrid? Micro means it's a smaller prototype of a grid. Just like the bigger grid, what are the constituents of the bigger grid? If you see, the generating stations will be there, transmission will be there, and distribution system will be there to the load. So basically generation is there, load is there. So here also, microgrid also will be definitely having generation, definitely will be having load. Here, suppose let us say Indian power system. Indian power system, just connecting generating stations to the load will not be suffice. There will be a lot of control involved here. Just like we have NLDC, National Load Dispatch Center, that controls the regional grids. And the regional grids, they again control the individual state grids through load dispatch center of the states. So this generation to load, when we are connecting from generation to load, also associated with it is control. So if you see here microgrid also, a group of interconnected loads and distributed energy resources with clearly defined electrical boundaries that act is a single controllable entity with respect to the grid. It can connect and disconnect from the grid to enable operation in both grid connector islanded mode. This is the US Department of Energy definition of microgrid. So coming back here. So just like we conventional grid, we have our conventional generating station. Here one term we use is DER, distributed energy resources. The reason is that the bulk power generating stations are located at a particular place, they are localized. But this distributed energy resources means they are distributed also. For example, anybody, anywhere can put a solar panel. That will be energy source. That is in distribution side. So the DERs are localized compared to the conventional generating stations. And the load is also there. And also it is a controllable entity. Just like in power grid, there is a control. And why there is a control will come in the subsequent lecture. So another secret is electric distribution systems containing loads and distributed energy sources such as distributed generators, storage devices, or controllable loads that can be operated in a controlled, coordinated way, either while connected to the main power network or while islanded. So two conditions will be there. I'll come back to that. So this is the microgrid, is the CRT, because I'll be talking about microgrid reliability. That's why I have taken this American Consortium for Electric Reliability Technology Solution, CRTS microgrid, for example. If you see here is this symbol is for PCC, point of common coupling, that connects to microgrid to the conventional grid. So this is the PCC. This symbol is the PCC, and this is your station switch, static switch, power electric switch. This is our transformer, and here of course energy meters will be there and different controllers will be there. So this is a typical microgrid. So what are the things? Here is a source. This PV panel is a source. The PV panel is a source. So here is the wind turbine associated with the windmill or wind generating station. That is another source. And it is a storage one, is battery is there. So here fuel cell is there. So these are nothing but the DERs, and the load. These are the conventional loads, and also will be controllable loads. So all these things they are in the microgrid. So if you see here, peer-to-peer control, any device can connect or disconnect independently, and operation of generator is locally controlled by group, and energy manager is to give initial set points, and high intelligence level is required. I'll explain how. Then unit out power control also will be there, and also we have feeder flow control will be there. I'll explain those things. So it is a European Union microgrid, because these are the typical microgrids. With respect to that, I'll tell about microgrid reliability. So European microgrid basically is a low voltage distribution systems with distributed energy sources, so micro turbines or fuel cells or photovoltaic, etc., together with storage devices like flywheels, energy capacitors, or batteries, and also we have flexible loads. And such systems can be operated in a non-autonomous way, or we can say islanded way. Autonomous way means islanded way, non-autonomous means grid connected way, or autonomous way or islanded mode. The operation of microsources in the network can provide distinct benefit to overall system performance if managed and coordinated efficiently. And there are two levels of your architecture. One, microgrid control center will be there, and means basically here microgrid control system establish set points for technological and commercial purposes, and local control will be also there. Both controls will be there. Overall control will be there. Central control is your microgrid control center, and also one local control will be there. So that I'll explain here. So this is basically another one I'm showing you is that here if you see here, this is a typical microgrid network. You see here we have a wind turbine as a source, and because these are variable generation supply. So in order to make it is a particular frequency and voltage, we have power electronics converter here, and also suppose if industrial user uses a load, and here is a micro turbine. Here also the variable generation is converted into fixed frequency and voltage power electronics devices. And similarly, energy storage, either charging or discharging, involves a power electronics device. And also this is another load, and here DC sets, the digital generator sets, and this is a residential user or consumer. Here photovoltaic cell is there. So basically if you see here that we have distributed generation, here wind is there, micro turbine is there, PV is there. So these are nothing but distributed generations, and loads are there. Here is a industrial load is there, commercial load is there, residential load is there, and storage device is there. Here is the battery storage, or here also controls will be there, because this power electronics requires control and overall system requires control. So another will be the PCC, point of common coupling. Here is the PCC that connect to the utility grid or conventional grid. So now, just to have an idea, we have limit values for synchronous interconnection between microgrid and main grid. Suppose you are distributed, I am writing distributed generation or distributed DER. So if it is from 0 to 500 kVA, the frequency deviation allowed is 0.3, and delta V is 10 volts, and this is the angle in degrees. So if you see here, as we go more and more in capacity of the DER, the allowed deviations will be less, if you see here. So that's why the stringent requirement, this operating grid for operating in a grid connected mode. And if you see here, the micro system reliability versus financial cost, this is the total cost, and this is the cost for investment, and means capital cost plus operational cost, and this is the cost of interruption. Cost of interruption. So this cost of interruption is related to the reliability. So when the supply reliability is more, your interruptions are less, naturally cost of your interruption will be less. That means if you go for higher reliability, what will happen? Your total cost will increase. As we go for more and more reliable electricity, the cost of investment will be also increasing. So how much reliability we need, it depends on application. And power system is known for its legacy reliability of 4 nines, means 0.99999, 4 nines, and sometimes we say 5 nines, US and all they say 0.99999. That is the reliability of conventional grids existing today. So when we go for more reliability, and that's why the investment cost will be also more. So here some examples, I'll come back later on. Economics benefits of it, this is basically European one. I'll come back later on to this slide. So I'll come back later on to 3 slides. So what are the benefits? Why we are going for the microgrid reliability for our discussion? Here, if you see here that the microgrids are able to do either in islanded mode or in grid connected mode. So here the reliability will be significantly enhanced if we do properly. So reliability aspect we will discuss, and also efficiency will be also better because we don't have any transmission lines. The load is connected to the generation on site and locality, and there will be economic savings, and also there will be sustainability because DERs are mostly sustainable sources or renewable sources. So now I'll come back. What is reliability and how we are going for microgrid reliability? So that this is the conventional definition of reliability. Reliability is the probability of a device performing its purpose adequately for the period of time intended under the operating conditions encountered. So what I'll do is that I'll take a very simple example first, then I'll come back to microgrid so that when we have captured what is reliability, how it is being done. So with a simple example, I will first cover. Then what I will do is that then I'll come back to the actual microgrid reliability. So this reliability definition has four principal components. One is probability of a device, or also it can be per system. Then performing its purpose, and then adequately performing its purpose adequately. This is another aspect. Another is your time intended and under the operating conditions and covered. So I'll give a simple example first, then I'll come back to the microgrid so that understanding will be better. So what is the meaning of probability? Let us say that I am taking over the conventional bulbs. What is the reliability of the bulbs? So what I'll do is that how reliable of the bulbs. Suppose I am any company bulb I am purchasing. Let us say that I am purchasing the Philips bulbs, and I want to know what is the reliability of Philips bulbs. So what we do is that usually you take the failure pattern. For simplicity, I have taken 100. So let us say that number of similar bulbs, Philips bulbs, we have taken into consideration 100. And I am seeing that after 100 hours, 3 bulbs, the probability of bulbs performing or glowing properly after 100 hours will be here nothing but how many have failed? 3 have failed. So 97 are surviving. So the probability will be 0.97. Of course, this probability will be calculated in different ways. I am just giving an example. So the probability that the bulb will be working after 100 hours will be 0.973 may fail. So now, purpose. What is the purpose of the bulb? The purpose of the bulb is to give certain illumination. Lumens will be given. Let us say it's a 250 lumens. So that lumen should be there at a prescribed frequency. Suppose our designed for a single phase system, 230 volt with 50 hertz. So we should get this lumen, whatever lumen is being specified. If the illumination is very low, under such condition the device is not performing its purpose, because the light will be dim. We cannot read with that light. So similarly another example is that peak load generator has to supply load during peak hours. If it is failing to supply during peak hours, then it is not performing its purpose. Same way, time intended. For example, a transformer is supposed to work continuously, and if it is failing to do so, then it is not performing its function. A peak load generator is supposed to work only during peak loads and not during all the time. So that's why if it is during the peak load, if it is working, we say that it's doing its performance during the intended time. Similarly, operating conditions. The operating conditions for different devices vary as per the requirement of the system. For example, submersible pump is supposed to work within the water or inside the water. If it is working on the surface but not working within the water, then we can say that it is not working under the given operating conditions, because the pump, which is submersible in nature, should work when it is inside the water. So fan is an indoor equipment, and you should evaluate its performance when the fan is inside the room where we have fitted. If you put outdoor, the same operating conditions is not fit for which the fan is designed. So now I'll come back to microgrid. Same thing, I'll come back to microgrid. So basically here, the reliability of the microgrid is the probability of a microgrid performing its purpose adequately for the period of time intended under the operating conditions and covered. So we must know what is the purpose of the microgrid. What is the purpose of the microgrid? We say that it's doing adequately. And what is the time under which the microgrid should operate, and what are the operating conditions? So coming back, if you see here, then how to calculate probability is the mathematical aspect of finding the probability. So now, what is the purpose of microgrid? I'll come back with a slide of microgrid to explain what is the purpose of microgrid so that we understand. Here is a microgrid. So if you see here, the very purpose of microgrid, or you can go to the very definition from which we can know what is the purpose of microgrid. So if you see here, the electric distribution system containing loads and distributed energy sources such as DERs, and also storage device and controllable load that can be operated in controlled, coordinated way, either while connected to the main power network or while idle. So both definitions say the same thing. That means that microgrid has a purpose of, here is a microgrid, is a purpose of, there are loads. So the load should be met using the DERs if this switch is open. That is islanded conditions. Means it has the ability to supply all the loads, or some priority loads will be there, which we will have intelligent islanding for that. So that is the purpose. And what is the probability of meeting that purpose? We'll discuss that. So that is the purpose. The purpose of microgrid is to provide the power using the DER, and that has to be done both when to the grid or when it is in the islanded mode. Next is for the time period intended. This time period intended will be having significantly different significance in microgrid. For example, this time period can be islanded time period or can be non-islanded time period. Because islanded time period, we have to see certain aspects. For example, if our DERs are not sufficient to supply the load, we can have intelligent load shedding. Now, operating conditions. What are the operating conditions for the microgrid? Operating conditions, for example, for that purpose only, I have given this. This is the operating conditions. The deviations cannot be outside of this boundary. Frequency has to be within certain boundaries. Voltage has to be within boundaries. Power factor has to be within boundaries. Means this is the purpose it has to meet. Means power with this quality in terms of frequency, voltage, and power factor, and also in terms of reliability. Means it should be reliable power. It should be reliable power. Means power should be continuously available to the loads. So this is about this definition of reliability with respect to microgrid. Now, there are certain important terminologies that we have to see here. For example, failure. A failure is an event when the system is not available to perform its intended function under the specified conditions for the specified operation time. So this is called a failure. For microgrid, we understood what is its intended function, and we know what are the specified operating time. If the microgrid is not able to do its function, then it is a failure. Then comes failure rate. The number of failures per unit time is called failure rate. For example, failure rate is items failed or number of times failed, particular within a total operating time. So this is the failure rate. And repair rate. Many systems are repairable systems. Means once failed, if we make some repairs, again it will be operating. So in that case, we'll be also involving another is called repair rate. So number of repairs per unit time. So another term will be coming across is mean time to between failure, MTBF. The average time between failure occurrences means how much time. I'll come back. Another slide is there where we can understand this in a minute. So if you see here, I'll come back to this MTTR availability, unavailability with this figure. Let us say that here is the time and here is any unit. Let us say it's a microgrid is there and we are seeing the microgrid operation with respect to time. Now, let us say that the microgrid is operating and the failure occurs after, let us say, 1000 hours. So time to failure, first failure is how much? 1000 hours. And the repair takes, let us say, some 20 hours. So what is the total cycle? 1000 hours plus 20 hours. So time to failure is for the first failure, the time to failure is 1000 hours and our repair time is 20 hours. So this is the idea. So if you see here, first TTF is 1000 hours, TTF1 is 1000 hours, and TTR1 is 20 hours. Means this cycle is nothing but 1000 plus 20 hours. So that is your MTBF, mean time between failures. Similarly, now after first failure and repair, again there will be some time after which the microgrid will be failing. Let us say that second time when the microgrid is failing is, let us say, it is after 800 hours. And the time taken for the second repair is, let us say that time to repair is, let us say it is 40 hours. Like that. Similarly, TTF will be there. Let us say it is 900 hours. And TTF or TTR3 will be, let us say it is 30 hours. Like that. So what happens is that we have history of different microgrids operating. So we have time to failures and we have time to repairs. So this time to failure 1, time to failure 2, time to failure 3, like that. So we'll get a mean time to failure, MTTF. So we have discussed that is MTTF, mean time to failure. So what will be my mean time to failure? TTF1 plus TTF2 plus TTF3 divided by n number of failures if we have taken. So that is mean time to failure. So now your repair will be there, TTR1, TTR2, TTR3, like that. So similarly here, TTR, suppose n number of repairs we are saying, so all TTS combined, TTR1, TTR2, like TTRN divided by number of repairs. So that is called MTTR, or mean time to repair. So this is called failure repair cycle for a repairable system. So similarly for microgrid also, it can be for the whole grid, it can be for a component. So anything can be possible. So this can be for a whole microgrid, or this can be for a component of the microgrid, so from which we can get the system reliability. So this is the basic idea. So mean time to repair is that average time to restore the system, as I told you, TTR1, TTR2, TTR3. Suppose n number is there. If we divide, MTTR is nothing but 1 by n into TTRs combined together. So similarly we have MTTF and MTTF and MTTR is called MTTF, mean time between failures. This one failure plus one repair is one cycle, MTBF1, MTBF2. Similarly, if you time between failure is TBF1, TBF2. This is the TBF1 is first cycle, TBF2 is second cycle. So we got mean time between failures also, like that. So now coming back, another availability. So availability is a measure of time the system is actually operating versus the time that the system has planned to operate. This is applicable only for a repairable system. And unavailability is the measure of time that a system is not operating versus the time the system has planned to operate. This is applicable for a repairable system. So basically, microgrid is a repairable system. So I am taking the repairable system example for our sake of discussion. So coming back, so basically, reliability we evaluate based on the failures. Reliability we do not evaluate based on, so based on the past history and all, we get this reliability calculations. How we do it practically, we'll come back. Now here what happens is that there is a general reliability function. If you see here, now I am giving a simple example, and of course mathematical rigor will be more. I'm not touching any mathematics here because our time is very short. I just want to give an overall perspective. So I'm going back to the bulb example. Total number of bulbs we have considered is how much? 100. And number of components surviving at T, let us say 100 hours, after 100 hours, is how much? 97 hours, because the number of components they have failed is 3. So 100 bulbs, out of which after 100 hours, let us say that 3 have failed. So at any time, number of failed components plus number of surviving components is equal to nothing but the total number of components you have taken into consideration. So in a simple way, we can say that how many reliability is the number of components surviving at any given time. It is a simple example. Of course, mathematics will be more rigorous reliability. So basically, reliability is how many are surviving with respect to the original one. So this is RT. So this reliability is always a function of time. And this function of time, basically this is for a particular case where we assume that during the normal life period, the failure rate is constant, for which the reliability is e to the power minus lambda t, where lambda t is the failure of a component or failure rate of a component or a system. So if the failure rate is constant, it is nothing but e to the power minus lambda t, and mean time to failure is nothing but TTF1, TTF2, like that, TTFN, and divided by n, and mean time to repair is this TTR1 plus TTR2 plus TTRN divided by n. This is what I have again shown you, time to failure. Here your TTR, MTTR plus MTTF is TTA, your time between failures. So I'm not going for here. If you see here, MTTF is 1 by lambda, where your 1 by lambda is your repair rate, and TTR is 1 by mu, where mu is the repair rate. If it is a repairable system, the availability is nothing but MTTF divided by MTTF plus MTTF. So for all the reliability, basically the data we must know is that what is MTTF, what is the value of MTTF, what is the value of MTTF, and based on that, we'll be finding out what is the availability probability and what is the unavailability probability at any given time. So this is called the typical bathtub curve in reliability parlance. So if you see here, we have, this is one is decreasing trend curve, this is the constant value curve, part of the curve, and this is the increasing part of the curve. Infant mortality, or A phase A, this is the useful life, which is a longer period, this is the stage. You see here, the first phase, A phase, a burn-in phase, and failure, if you see here, that is decreasing, initially too high and is decreasing. The reason is that manufacturing defects, welding, soldering, assembly errors, and different parts, what happens is that after commissioning, we take care of that, after acceptance testing, burn-on testing, screening. So what happens is that the failure rate decreases and stabilizes to a normal value. So during normal period, usually the failure rate is constant. When the unit gets old, what happens? So useful life is this. If you see here, A to B is here, burn-in phase or infant mortality phase. Now, next is useful life period is B to C. The useful life period where the failure rate is almost constant. Here, the environment, random loads, human errors, chance, events, etc., possible causes. But here, how we can improve reliability? Here also, this will be a zone, but almost constant. Possible improvements is that redundancy and robust design. Those things we'll discuss. How we can enhance the reliability of microgrids. And then last stage is here, wear and stage. Fatigue, corrosion, aging, friction. So here we can do is that derating. We can operate at a lower rating, and we can do some maintenance, or we can go for some replacement of plant. So this is the phase. So our reliability evaluation of engineering systems basically deals with this useful life. So all the reliability investigation basically we are doing is for the useful life period. Now I'll come back to the reliability indices. Before I go for reliability indices, I'll give you what we are going to do here. So I'll be telling about, because this indices will tell about the reliability of the microgrid. So what I'll do is that I'll have an overview first of all these indices, then I'll come back to the particular cases. So in reliability, particularly our power system reliability, in which the microgrid also comes, we talk about two types of reliability. One is called adequacy analysis, reliability based on adequacy analysis. Another is your reliability analysis based on security. So adequacy analysis means basically what is the reliability for a power system. As I am saying that power system is a legacy reliability of 0.59, 0.99999. So 5 nines. This much of reliability of our power system is now attained. So now, if this is the power reliability, so basically that, and the peculiar nature of electrical energy is that whatever is the load demand, exactly same we have to provide, so that your generation meets the load with the losses in the system. So it's a very stringent requirement of control. So when the load demand is there and generation cannot meet, that is called loss of load. We cannot, because load demand is there, our generation is not sufficient. What happens is that we lose some load, or we lose reliability in terms of not able to provide power to the load. Are you getting me? Here, loss of load probability means loss of load means load demand is there. My generation is not sufficient. Why my generation will not be sufficient? My system design was that I will be meeting the load. But many times there will be random tripping, means because of fault or because of some other thing, because of fault and unforeseen reasons, the generators will be tripping. So that time the load demand will be more, but generation will be less. So we cannot meet the load demand. So usually in conventional reliability analysis, what we have is that we have we say that HL1, hierarchical level 1, hierarchical level 2, and hierarchical level 3. Hierarchical level 1 is called generation reliability analysis. Generation reliability analysis means what we assume is that, let us say that we have a generation and we assume that there is no transmission line. We are connecting the load to the generation station and we see whether the generation is sufficient enough to meet the load. And if not, how much we are not able to do. So loss of load probability basically is that HL1 or hierarchical level 1 reliability analysis. Now in micro, what do we have? We have aggregation of generation hierarchy, transmission hierarchy, and distribution hierarchy. In microgrid, we have 3. Of course, transmission is not there because the local loads will be provided by the generating units. So we have generation level of HL1 is there. We have HL2 we are not having, or transmission system we are not having because we are directly feeding to the load. So we have hierarchical level 1 or distributed energy resources are there. DERs are there. They are providing to the load. So we have 2 sets here. We have HL1 analysis, which is generation reliability analysis. Also, we have HL3 analysis, which is distribution reliability analysis. So now I am talking about HL1 analysis or hierarchical level 1 analysis or generation reliability analysis. Here, DERs are providing to the loads, whatever load is there in the microgrid. And what happens is we are saying that when it is in grid connected mode, whatever is requirement you can draw from the grid. But it is in islanded mode and my load demand is more. My generator is one of the DER strips, or it is not operating because of this fluctuating nature of the DERs. So what will happen is that some load will not be able to provide power or energy. So in that case, loss of load will be taking place. So this LOLP is more prominent in the islanding mode. So loss of load probability, so the is higher than the capacity, and higher than the capacity because of the random of the loads. This index does not give any information how much is the difference between capacity and demand. It is usually measured in hours per year, and because it's just a probability. Just a probability means how here. This I'll explain with an example. So loss of load probability means how much was the probability not meeting the load. Mathematical analysis I'll come later. If you see here, if you see here, this tau t is what? Tau t is 0 if your CT is your generation capacity at time t and LT is the load at time t. Here capacity or your available generation is greater than the load, greater than 0, equal to 0 means at least the generation meets the load. Equal to means CT or generation is equal to load. Then the CT is equal to LT or CT minus LT is equal to 0. Or greater than 0 means generation is greater than the load. So we are able to meet the load. If we are able to meet the load, that means tau 2 is 0. There is no loss of generation. So tau 2 is 1. When it will be 1? When generation is less than the load. So that's why generation minus load is less than 0, less than equal to 0. Means equal to 0 will not be there, sorry, less than 0, because equality is here. The typological mistake, please forgive me. So it is less than 0. When the generation is less than the load demand, that time tau 2 will be 1. So we see how many intervals do not meet this requirement. During how many intervals the generation is less than the load demand. So here NT is the number of time units. For example, each minute we are studying. Per minute wise or hour wise. So every minute we are checking whether the generation is less than demand or generation is less than more than the demand. So accordingly, how many intervals the generation is less than the demand. For example, let us say 1 hour is 60 minutes. Each minute I am checking, and I see that 3 minutes in an hour, it has not, the load has been not been made by the generation. So 3 by 60 will be the probability. 3 by 60. 60 is the, or I say 100 hours I am checking. Within 100 hours, if 4 minutes or 4 intervals or 4 minutes, the load was not supplied by the generation. So this dot E was 1 for 4 times. Each dot E is 0 if CT is greater than LT. First interval satisfying. So it is 0, 0, 0. But where it is not satisfying, it is 1. So how many times 1? Let us say 4 times satisfying. So 4 by 100. So 0.04 will be the LOLP in that case. That is measured in hours per year or days per year. So this is about loss of load probability. The DR or distributed energy resources are not able to meet the load demand, then only the loss of load probability will come into picture. Then loss of load expectation. It's nothing, it is a variation of LOLP. It describes the average time when the generation is lower than the demand. It is also measured in hours or days per year. In many cases, it is used to simulate penalties for electricity interruption. This index also does not give any about, I'll explain this, about how much is the difference between capacity and demand. So LOLP is nothing but whatever LOLP we got here, whatever LOLP we got, and if we multiply with the time interval, for example, if T is equal to 365 days, the load model is a daily load curve through a year. The LOLP will be nothing but here, each unit is a day, 1 day, 2 day, up to 365 days, and LOLP into T will be nothing but the LOLE. So this adequacy analysis doesn't say that what is the difference between the capacity and load. Just the load is not meeting the demand, then we say that there is a loss of load. For example, load is 100 megawatt, and let us say that generation is 99 megawatt. So how much it is not meeting? It is not meeting by 1 megawatt, but still we calculate is a loss of load. Another is load is 100 megawatt and generation is suppose 60 megawatt. It's 40 megawatt difference is there. So these are two different cases. So for that, we have to have a different approach. That is called here. That's why another is called expected energy not supplied, or ENS. It is also called the loss of energy expectation, or LOE, or expected unserved energy, or EU. EU is slightly different, but same connotation comes. This index, rather than 2 explained above, gives an amount of energy. Sorry, this index, rather than the 2 explained above, gives the amount of energy not supplied to the customer when the load. So if you see here that ENS is nothing but CT is the generation and generation capacity, and LT is the load, and TOT is, as I am saying, whether it is able to supply or not able to supply. So based on that, how much basically energy? So we say that 100 megawatt hour was not supplied, or 10 megawatt hour was not supplied. So here we just a probability. Here we have just a probability. So that probability doesn't tell exactly how much energy was not served. Here we exactly know how much energy was not served. Suppose ENS is 100 megawatt hour. Another ENS is 10 megawatt hour. Naturally, 10 megawatt hour is a better reliable system than 100 megawatt hour expected energy not served. So this is why it is another index. So another is called loss of load frequency, LOLF, means it is measured in occasions per year. How many times we have not been able to meet the load. So here LOLF is nothing but Fi minus small fi, where Fi is the frequency departing system state and I is the departing system state. So what happens is that basically loss of load duration, next one is LOLD, is how much duration the load is not being met. So now this I told in a conventional sense, it is a hierarchical level 1 reliability analysis, and because the microgrid has both hierarchical level 1 and hierarchical level 3. So this is the hierarchical level 3 reliability indices, or distribution reliability indices. That is also being taken into consideration for a microgrid. This is the distinct feature between a conventional grid and your microgrid. In conventional grid, we separately do the generation hierarchy or generation units, and we have transmission reliability analysis, we have distribution reliability analysis. So microgrid combines both generation and as well as distribution reliability analysis in a suitable way. And because here there is no transmission, because it's a localized load. So what are the HL3 or distribution system reliability indices? Here, the relative indices will be based on customers or load. So if you see here, it's a very famous index that is called System Average Interruption Duration Index or SADI. This index measures the total interruption duration for average customer in a defined period of time. It is calculated dividing the all interrupted time by the total number of customers. If you see here, that total summation of customers interruption duration and total number of customers served. Let us say that we have 100 customers and customer work didn't get power for say 1 hour. So that's why, and another is your system average interruption frequency index. Here, just like the duration means how much time or how much duration this average duration for which the load was not served to the customers. Another is that your system average interruption frequency index. This index shows the average number of interruptions that customers suffer in a defined period of time. So this is called SAFI. So now coming back, another is your SADI, another is it is basically about the system. So this is about the system average interruption duration. I'll answer at the end because I have a thought of
Yes, sir.
or I have a train of thought while presenting. Maybe after 10 minutes we'll stop the presentation and we can interrupt.
Sorry, sir. We will put up the questions after completion of your presentation. We will put up.
No problem. Absolutely not a problem. Very nice.
Thank
You can
you,
share my email ID with all the participants.
Okay, sir.
And here also we can, if you wish, we can spend last 10 minutes or 15 minutes because I have to say certain things, important things still I have to cover.
Yes, sir. We will do.
To all of you, I need a.
Yes, sir. You are audible.
Yes. So if you have anything you can ask me, I'll be happy to do because it is a very short period in which I have to give an overview. So I was also in a little bit dilemma what to present, what not to present. So I'm trying my best to squeeze out the things in a most effective way. Hope. So coming back, as I told, these reliability indices based on distribution side or based on customers. Distribution side are directly related to the customers. And if you see here, again, it is passed toward system, whole distribution system, or in distribution system is not a microgrid here. So based on the overall microgrid interruption here, if you see here, from microgrid side, what is the duration for which the microgrid is not able to supply to the basically the system average interruption duration index. How much duration the microgrid was not able to supply to the customers or loads. Similarly, here the system average interruption frequency index, this index shows the average number of interruptions that customers suffer in a predefined period. So this frequency is also it's a system related frequency, how much frequency the system is not able to supply to the customer. Now, here another terms from the customer perspective, it is from the system perspective or microgrid perspective. From customer perspective, if you see here, customer average interruption duration index or CADI. This index is very similar to SADI, but based on the interrupted customers and not in the total number of served customers. If you see here, the difference is that it is based on only on the interrupted customers. Let us say that we have 1,000 customers, out of which only 10 have been interrupted, others were not interrupted. So those who were interrupted, whose power supply is interrupted. Only we are interested with those customers. So total summation of customers interruption duration, total number of customers interrupted, not the whole total of customers. So basically it is a measure of to the SAFI, that is CADI. Now customer average interruption frequency index. So this is very similar to SAFI, based only on the interrupted customers, like the previous case, not the total number of servers. So if you see here the number of customer interruption to the total number of distinct customers interruption. So another is called average service availability index. It is the ratio between the time when the customer have electricity supply and the time demand of electricity supply. Because maybe there when the demand it is not there. So that is your average service availability index. So I'll come back quickly that usually how do you do all these things in a series system, parallel system, and those who do not belong to series parallel system. All these things. And we all know any series system, let us say that a series system is there, any of the component fails, what will happen? The whole system will fail. So total reliability is nothing but the product of reliability. Any system is failed means reliability zero means total system will not be operating. So for example, a system consists of 3 identical balls, all of which must work. The system reliability means they are in series, 3 balls in series. So this is the RS. Any ball is not glowing or series circuit is not operating any component, then it will be system reliability will be zero. Similarly, parallel, any one of them survives, it will be there. So if you see here parallel system 1, total reliability probability. So it will be 1 minus R1 into 1 minus R2 into 1 minus R1. So if you see here, series case is 857375, parallel system is more. Usually parallel systems are more reliable because if one fails, other 2 will be there. So that's why parallel systems have their advantage. Now this is series parallel system and this is the equivalent series system. This parallel system if you convert to series and series parallel system. So this is about the simple system. The modern systems are not, yes, I'll share my PPT with all of you. These modern power systems are not just conventional series parallel systems. For example, I'll come. So in that case, we have different methods, like we have test space approach, we have Markov chains and all these things we'll be doing. Because we don't have much time, so I wanted to show you some simple example. So very simple example. We have a micro the wind generation, and we all know this variable speed will be there. So voltage and power will be variable generation. So we convert AC to DC, then we can either give the DC bus, and if we have AC bus, again we convert DC to AC. So this is simple microgrid. So components here is that your wind generator is one component, AC to DC component this is another component, and DC bus is another component, and DC to AC is another component, AC bus is another component, plus controllers will be there. These are components. So these components here, I'm giving a simple example. I'm giving a very simple example. This previous example. If you see here, wind farm, which is combined with the AC-DC converter. Again, we have DC-AC converter and load. So basically, it is a series parallel network. For example, wind farm. If you see here, AC to DC converter, DC to AC converter, load. Again, DC to AC converter, AC to DC converter. So if you see here, systems are in parallel, and so these 2 are in parallel. So it's a series parallel system. 1 plus 1 redundancy. 1 plus 1 redundancy means any reason, let us say that this converter fails. This converter fails. Or this converter fails. So what happens is that another path will be available to the load. So it is 1 plus 1 redundancy. Similarly, I am giving a simple example. Let us say that failure rate is 0.05. We have taken for a particular paper. So wind turbine generator failure rate per year is 0.05. And repair rate means repairs per year is in. So if you put values, their availability will be 0.992. So if you see here, here the formula is here, A1 is equal to nothing but 1 is the parallel system. So parallel system we have here. here, sorry, here parallel system is 1 minus suppose it's a parallel system 2, parallel system 1, 3, like that. So 1 minus R1, 1 minus R2, up to 1 minus R. And same thing we have here. So here this first one, second one, third one, everything we have done, and this is the failure probability here. Thus the failure probability or FOR for the model without redundancy is 0.08. Overall force outage rate is this much. So here microgrid is also said to be reliable if the generation meets the load. We use availability models to calculate reliability indices. So this is basically what I was saying is that HL1 model. Your generation model will be there, load model will be there, and based on which there is loss of load probability, loss of load and expectation, all this we do. So simple calculation. How we do in HL1? Giving a simple example. Let us say that we have a 3 megawatt units are there. Unit 1, unit 2, unit 3. Each having a force outage rate of 0.008. So what do we mean by force outage rate? Force outage rate, outage means when our microgrid or any component is not available for the service it is intended. So force outage is because of faults or some other reason, forcefully the unit goes out of operation. So the FOR or force outage rate is 0.008. This is the probability of not being available for generation. So now, how many units? You have 3 units. Each of how much megawatt? Each of 3 megawatts. And here, if you see here that all 3 megawatts are operating, how much it will be? 3 into 3 is 9 megawatt. And how much outage? None is out, so 0 megawatt. So what is the probability? What is the available probability? Failure probability is 0.008. So available probability is 1 minus 0.008. So it is 992. So 3 units are there. So 992, 992, 992. This is my available probability. So the cumulative probability will be nothing but 1 minus this one. So I'll explain this. Cumulative probability at the top will be 1. So how it will be, I'll explain. So now, any one of the unit trips or 2, 3 or 3 tips. What I have done is that my FOR, for simplicity of calculation, I have taken to be the same. FOR is same here. If FOR is same here, so 1 unit trips, how much megawatt will be losing? We'll be losing 3 megawatt. So how much megawatt will be available for us? Available will be 6. So if you see here, the probability will be here 0.008 here, 1 unit is which is failed, and 0.992 is that surviving unit, another is 0.992 is another surviving unit. Because there are 3 combinations, either 1 trips or unit 2 trips or unit 3 trips, that's why it is 3. 3 into this one. NCR formula will be using. So if you see here, this is the cumulative probability, I'll come later on. These are the probabilities. This is the probability. Similarly, what is the probability or 2 or 3 or 3 1 trip? So 1 or 2 trips, what is the megawatt outage? 2 units means 6 megawatt. And how much available? 3 megawatt. So if you similarly, if you see, this is the probability. Now, the probability that all units will be tripping simultaneously. So units will be tripping simultaneously means all of them are in failed state. So 0.08, this is my outage probability, 0.08, 0.08, 0.08. This is the probability. So the probability that all units will be tripping is this one, same. Now, cumulative is that what is the probability that outage will be 3 megawatt, 6 megawatt or more. If you see here, outage is 9 megawatt. Here megawatt is 6 megawatt. So this 9 megawatt is included in 6 megawatt outage. If I say the outage greater than 6 megawatt, means it includes 9 megawatt outage. It includes 9 megawatt. So that means this outage plus this outage taken together will be the cumulative outage. What is the megawatt, or what is the probability or cumulative probability that loss of load will be more than 6 megawatt? So it will be including 6 megawatt outage as well as 9 megawatt outage. So this summation plus this summation is the cumulative probability of loss of load or outage or capacity greater than 6 megawatt. Now, 3 megawatt and above will include 3 megawatt, 6 megawatt, 9 megawatt. So what is the probability that capacity outage will be 3 megawatt or more will be this plus this plus this. So if you see, this is the probability. And what is the probability of 0 megawatt more? The cumulative probability will be 1. So because we will be using this for calculation of loss of load probability or loss of energy expectation. Now, what is loss of load probability? I'll explain here. Here, capacity, we have 3 units, each of 3 megawatt. So my generation capacity is 9 megawatt. Generation capacity is 9 megawatt. And I have deliberately taken a load that my load, so my that you see on peak it is 5 megawatt, my off peak is 2 megawatt. So definitely my generation has been how much? My generation has been 3 megawatt of 3 units, 9 megawatt. But my load is sometimes on peak 5 megawatt, and when not peak it is 2 megawatt. So it seems that it is a very reliable system. But you will see that still there will be loss of load probability. How? The loss of load occurs when the load exceeds the capacity for an expected load L0 and the available generation CJ. The loss of load probability is nothing but the probability of your generation equal to the load. And what is the probability? For example, here there are 2 load levels. One is 5 megawatt for 3500 hours and 2 megawatt for 8760 hours. So now, what is my loss of load probability? What is my load here? 5 megawatt. So any outage which is greater than 5 megawatt will lead to loss of load probability. If you see here, when it is 9 megawatt availability, load is 5 megawatt, naturally there will be no loss of load. The generation is 6 megawatt or capacity available is 6 megawatt, load is 5 megawatt. So we will not have any loss of load. So whenever generation falls below 6, means it goes to 3 megawatt, that time we will have loss of load probability. And what is the cumulative probability for 3 megawatt or your 6 megawatt outage or more, or 3 megawatt capacity or less? It is nothing but 0.001907. 0.19007. And now, if you see here, what is the duration for which this probability exists? What is the total duration? My total duration is 8760. Total 8760 hours. And out of which, how much? 5 megawatt? It is only for 3500. Ratio of 3500, because this is the duration for which this load exists. So this factor is basically the generation not meeting the load. This you see here, if the capacity is 3 megawatt, my load demand is 5 megawatt. So this is the probability that load will not be made by generation. And how much, as far as probability of time is 3500 out of 8760. So this is my probability. Again, this is for 5 megawatt load. Similarly for 2 megawatt load. If you see here 2 megawatt load, my capacity is 3 megawatt. That time also there will be no load. So only when all the generators trip, that time only I will be having a loss of load. What is the probability that all generations will be, all generators will be tripping? This is the probability. If you see here, this is the probability we have taken. This is the probability, this value I have rounded off. So into here, how much is the duration? If you deduct 8760 minus 3500 is here, this is the 5260 divided by 8760. So this is my loss of load probability. So probability that the microgrid having 3 wind turbines, I am assuming that would be a consistent generation. I am not talking about the variability. For that, again, we have to go for another analysis. So we see here, it seems a very, very simple thing that we have 5 megawatt peak and 2 megawatt off peak period. and we have a generation of 9 megawatt, definitely it's a very reliable system. But if you see that it's not, still there will be loss of load probability of these values. So another is that this is for series parallel systems we are talking about. And suppose we don't have many complex systems, we cannot just put into series parallel. So we approach, that is called also some Markov process will be there, and we will be state space. And here what happens here is that I'll explain a simple example, then I'll come back to the, if you, we can have a sunny day or a rainy day. So sunny day means we are having rains, sunny day means we are not having rains. Okay? Usually nobody can exactly tell whether there will be a rainy day or there will be a sunny day. We can say that probability of rainy days, there is a probability that, or we can say that rainy day will be there with some probability, or sunny day will be there with some probability. So here, for example, whether we are saying that probability is that rain will be tomorrow, it will be rainy day, and 60% probability is that rain will not be there. So total probability is 1, and not raining today. 20% is rain tomorrow, and percent that no rain will be tomorrow. So how I have put this in the Markov model? What is the Markov model? We said it's a memoryless model. Means, coming back here, I'll just see here the system characterized by lack of memory. That is, future states of the system are independent of all past except the previous states. So that is called a Markov system. Why? Because in power system usually the present state depends only on previous state, not previous to previous state. That's why it's usually done as a Markov process. So in this case, if you see here, how much here, if you see here that rain and no rain, that's rain and no rain, I have represented in terms of these probabilities. So 60% no rain tomorrow. So no rain, the transition from rainy to not being rainy is 0.6. If you see here, this 0.6. Now, if you see here that 80% no rain will be there. So self probability of not being rainy is 0.8, and the transition means 20% rain may be tomorrow. The chance of no rain to rain is there. This transition is 0.02. 60% no rain tomorrow means, or 40% rain tomorrow. This is a self probability. So rain tomorrow, no rain tomorrow. If you see here, whole thing model. So these are not state probabilities or state probabilities. State of being in rainy state, state of being not being in rainy state. Two states we have considered. Similarly, in reliability, we have two states: operating state and failed state. And also, what is the probability of going from operating state to the failed state? So this is what transition matrix is. If you see here, there is a self probability 1 being in one state, being in two state, state 2. This transition, just like we say P11 means probability of being in one state. P12 probability of gliding from state 1 to state 2, and P21 probability of transiting from state 2 to state 1, and P22 probability of being in state 2. So whole thing we say is your stochastic matrix. So rows, if you see here 0.4 plus 0.6 is equal to 1, 0.2 plus 0.8 is equal to 1. So rows sum up to 1. Markov process, same thing I'm telling here. This mathematics time I wanted to do here, the mathematical treatment. So what happens is that in Markov process we have basically what we are doing is that we are the probability of being in off state, probability of being in down state. So this is the physical reliability probability. This is your or availability probability. It is non-availability probability. So this non-availability probability is on reliability, and availability probability is here, this one. So how we calculate? If you know mu, if you know lambda, and then we can calculate. So same thing with microgrid. For example, so Markov model for the microgrid. State 1, Wind turbine is state, rectifier is in off state, inverter is in off state. Here coming back, and just I'll tell you about the system. So AC converter is rectifier, AC to AC converter is your inverter. So wind turbine is in off state, this is in off state, this is in off state. It's all three are working, or there is a chance that any one of them may not be working. So what is that markup process that we are going to discuss here? Here three components is there. Here wind turbine, that variable generation is being rectified using AC to DC converter and inverted back to AC power using a your inverter. So all these three are in off state, is state 1. Now state 2 is your wind turbine is down, rectifier is working, and inverter is also working. And state 3 is that wind turbine is off, rectifier down, inverter off. See here, state 4 is wind turbine off, rectifier off, inverter down. Here state 5 is wind down, rectifier down, inverter off, like that. Because three components are there, 2 to the power 3 is equal to 8. 8 states can be possible, and we also know what are the different transition rates. If we know the wind turbine, what is the repair rate of the wind turbine and what is the repair rate, failure rate of wind turbine. If you see here all three were working. Wind turbine was working nicely, rectifier was also working properly, inverter was also working properly. If you see here, that wind turbine failed. So failure, lambda wind turbine generator. So wind turbine is in down state. And if it is repaired, it will go back to the state 1. So this is the failure probability or failure transition probability. This is the repair transition probability. So wind turbine is failing, coming to this state. We are repairing the wind turbine, going to this state. Now, if you see here, what is going to the failure here? That here inverter is failing here because of the inverter tripping or failing. State 4, wind turbine is on, rectifier is on, inverter is down. Similarly, here off state, inverter is off and this inverter is down. Here also, if you see here again, rectifier is down, rectifier is off. This way we can have a Markov model. So now coming back, so alpha equal to alpha is a stochastic transition calculation we do. So calculations I'll explain a little bit here. So this is my Markov model for the microgrid having 3 components. So when number of components increases, this type analysis becomes difficult. So what do? We go that another is called simulation techniques. We have Monte Carlo simulation and other simulation techniques for that we can use for simulating the microgrid performance, and in terms of performance we can go for microgrid reliability. So here what happens is that alpha p is equal to alpha, where alpha is a limiting state probability vector or steady state probability vector and p is the stochastic transition vector. So these state probabilities are nothing but steady state probability vectors. If you see in this state, this state, this state, this state, each state probability vectors, and these are the transition probabilities. These are transition probabilities, these are state probabilities. These are state probabilities and these are transition probabilities. So if you see here, the relationship is alpha p is equal to alpha. So where p is the stochastic transition probability matrix, this one, and alpha is the limiting probability or state probability matrix. So if you see here that all the state probabilities will be 1. So how you do that? So this is the stochastic transition probability matrix. So here if you see that here wind turbine, I explain here just a minute. One minute, just a minute. Sorry. So consider that can be in 2 states, either in off state, this is 1 is the off state and 0 is the down state. So consider a component that can be in two states. So three components we have. We have wind turbine, we have load, wind turbine, we have rectifier, we have inverter. So three components are there. Let us say that any of the component, either it can be in working state or failed state. So here I am taking that up state is x is equal to 0 and down is x is equal to 1. After means failure I am counting as 1 and up I am counting with 0. After failure the component is repaired and returned to the service. The states and possible transitions are shown below. The probability of being in one particular state at t plus delta t depends after delta t time that how it is. Suppose this let us this is my transition probability is lambda is failure turbo lambda into delta t time lambda delta mu delta t is your transition from a failed state to the on state. So this is your state probability of being in zero, your on state or off state. This is the probability of being in on state. We are using here. Now, if you see here, what is the probability of being in P0 state or being off state at t is equal to t plus delta t. So if you see here, it is nothing but this is the thing. And what is the probability of being in failed state? This is the thing. So failed state probability and your on-state probability are dependent on initial probability or off-state probability, down-state probability multiplied with this lambda and mu. So whole thing, if you see here P prime T, P0 prime T and P1 prime T, this is what we have written. So this is the stochastic. So coming back, so these are the state probabilities. What is the probability of being state 1? Means all the components being in off state, and these are the all age state probabilities we have found out using this. So the probability of the wind system in off state is this one. Probability of is in down state is this. Total will be 1. So here some mistake is there. Just 2. It will be 2. 5 to some mistake is there in the calculation. I didn't see it. So now coming back, I'll summarize that. So I would like to say is that I told in a very nutshell because I'll come back to one of the previous slides. Few minutes I spent with that. Yes. Why we reliability is a function of because more reliable is the microgrid for which we have to have more investment. So if we have to have more investment, so how much investment we will go, how much reliability, that is called design reliability. So if you see here, the economic benefits, comparison of microgrids in European level, because this is the data we have already that I am showing here. It is nothing but this is your how much interruptions means how many what is the probability of not meeting the load demand or outage is your Q in hour per your annum, and it is European unit, so that is euros per annum. So these are the things. If you see here that cost model, maximum cost model, and minimum cost model, there are 3. So if you take the maximum cost model, so this is the maximum cost model. If you see here that here load is increasing. If you see here is the load demand in kilowatt, and all this is your outage probability. So if you see here that if we take maximum cost model, the cost is increasing with the less outage and more load. This is the thing. And similarly for your minimum cost model, if you see here, this is the minimum cost model, and this is the this is the maximum cost model, average cost model, and minimum cost model. Details I will not be able to explain now. Time is short. So what I want to say is that I'll say yes, Mr. Sahil, you have a question? Yeah.
Yes, sir. You can conclude.
Somebody. Okay. So I think within 2-3 minutes. So that is the idea. If you take a comparison of all these things, what is the comparison we will be getting is that, so the benefits will be that reliability of microgrid is much more compared to the conventional grid. Reason is being that most of the failures takes place in transmission line exposed to the atmosphere, and they are over kilometers, hundreds of kilometers. And here is the localized load. But here the unreliability comes during the islanded period. Yes, I will share the PPT to Dr. Subha, and he will share with all of you. So this is about and efficiency also. And actually, I wanted to tell one of my major work is islanding detection, because mostly we have worked in islanding detection and also we have done in microgrid reliability. So this is why what I was thinking to speak something about. We are using actually micro PMUs, phasor measurement units. Micro phasor measurement units are basically for distribution system. So these micro PMUs we have used for detecting the islanding, because if we detect the islanding, we can for what do we say, intelligent load setting and other things. So this is why what we have done is that we have done quite considerable work in islanding detection of microgrid. We have the paper in IT Smart Grid, IT Generation, Transmission and Distribution, and other journals. So I wanted to share certain things, but the time is short. So I'll conclude once again here. I'll come to conclusion. So conclude that there is a system of reliability, particularly this is a very good book. Yeah, this Nicholas Hajar, the microgrid architecture and control, and also some things we have taken. Bansalji's book also I have taken as a reference. I had also. So coming back here, so this microgrid reliability, basically the more crucial is islanded means is working as an independent unit. Also nowadays we have, you all know what is VPP, virtual power plants. And the difference between virtual power plants and microgrid is that microgrid we take as a localized control unit, whereas virtual power plants, they may be at different locations, not at the same location. So this VPP reliability is different from microgrid reliability. So not much time is there. So that's why I'll conclude. So anybody has any questions, you will ask now or later on, whatever you decide. Yeah. Anybody has anything?
Yes, Dr. Mohanta, thank you so much.
Thank you,
for
sir.
your. Yes, Dr. Shubho, please proceed.
Thank you, sir, for your insightful and knowledgeable presentation. We had learned various things like basics of reliability, various reliability indices like LOLP, as well as we had learned about how to use Markov transition matrix, state transition matrix to determine the reliability of wind power systems. So thank you, sir. I like to hand over Dr. Gurfran Ahmed. He will put up the questions before you.
Sure.
Thank you so much, Dr. Shubho. Thank you, Professor Mohanta, for your this presentation and in-depth and very fundamental analysis of your work as well as the research work. Yes. So on behalf of our participants, I will ask few questions they have put. How to deal the resilience in MG?
Resilience.
Yeah, how to deal the resilience in MG? Yes,
Resilience.
in MG.
Okay, just give me a minute. If you give me a minute, I'll have some resilience. I'll just show you. I have resilience. I'll share activity. Just a minute. Just you give me. I'll just share with you. Just a minute. So basically, resilience is nothing but ability to withstand the, suppose any failure takes place, how we are able to come back to the original system configuration. That is basically resilience. So how we go for resilience? So in microgrid, basically the resilience, we say it's more resilient compared to the conventional grids. So why? How it is more resilient compared to conventional grid? In conventional grid, for example, any transmission system failure takes place. So you all know when we, because I basically am from a protection background. So we all know that, let us say that any transmission system failure has taken place. So what will happen in that time? We have to first of know where the fault is, and the team has to go there and repair it. And so really, that's why the power system sometimes very poor, particularly the natural disaster and all. Now, here the resilience in microgrid, two types of resilience we have. We have, just I'll tell you, because I was because this lockdown, otherwise we are having to have a GAN program with our GTD smart grid, and also IEEE smart grid editor-in-chief both have agreed, but we cannot have the GAN programs because of this ongoing scenario. But there, I am talking about the resilience. I'll just a minute. 1 minute, just a minute. So what happens there is I'll share with that. I was thinking about telling about resilience, but somehow I thought that may be not so. As my So what happens is that what we do is that resilience, basically we have three types here. If you see here, planning for resilience, one is here operational planning. So this is resiliency, basically the similarity between resilience and similarity between reliability. So the basically DERs are there in microgrid. So what happens here is that reliability, security, and resilience indices are all interconnected, and they have to be investigated in a holistic way. So what is resilient? More resilient is one that has ability to sustain and recover from high impact events, whereas a more reliable grid is one that has fewer and shorter events. So what happens is that, what is the essential difference between resilience analysis and reliability analysis? So resilience analysis is basically aimed at that if you want the system to be more resilient, means it has the ability to sustain and recover from very high impact faults, very high impact events. For example, that one cyclone comes, it's a very event, and how quickly it can come back to its normal operation. That is called resiliency analysis. And reliability is basically usually connoted as the reliability is basically, our grid is more reliable with a fewer and shorter interruption. That small duration interruption, and also your very few number of interruptions. So thus resilience and reliability need to be suitably blended for optimal security. So what happens is that in resilience analysis, we have three things. One is called resilience enhancement, and that basically resilience planning, and another is resilience response, another is resilience restoration. So what is resilience planning? Resilience planning is also called as resilience hardening. For example, I was saying there that we have two sets of your rectifiers and two sets of converters. Because one fails, other will be taken. That is sort of redundancy reliability analysis, or that is sort of resilience hardening or resilience planning. And another is called resilience response. Another is called resilience restoration. So resilience planning mostly focuses on improved infrastructure. For example, our infrastructure, we have two sets of rectifiers, two sets of inverters, so that one fails, other will be taken care of. That is called improved infrastructure. And resource allocation, that is resilience planning, also includes resource allocations and proper maintenance scheduling. And resilience response involves operational strategies when a taking place how we respond to that catastrophic event. That is called resilience response, and it involves operational strategies throughout the smart metering or your situational awareness using micro PMU, preventive responses and emergency responses. This is called
Professor
resilience
Mohanta,
response.
I am very sorry for interruption, but our next speaker has already joined, and your presentation has been enjoyed a lot by our participants,
Okay.
and they are demanding high for your sharing of your PPT. And I am very sorry for the participants also. I cannot take more question. I will take only last question. What value of SAIDI and SAIFI is said to be reliable?
Okay, coming back just a minute, I'll come to the PPT. If you see here,
so briefly explain.
Just I'll share with the expressions. It will be, you can appreciate. The reason I'm adding how it is being done. If you see here that the sadi coffee, so this depends on number of consumers being served. So what kind of distribution system it is? So here, if you see that, let us say that we take 1,000 customers. We take 1,000 customers, and here, if you are talking about Safi, the total number of customer interruption out of 1,000 customers served, or total number of 1,000 customers served, total number of customers interruption. Let us say that 10 customers are not being served. So the Safi will be 0.9. Sorry, 10 by 100, 0.1. So it depends on which distribution we are taking and what is the type of load. It is a priority load, non-priority load. For example, if we are taking a rural distribution system, where we are talking about lighting loads or like that, so their SAFI can be moved. But if we are taking a system where we are preparing some medicinal factory, their SAFI has to be low. So it depends on where we are serving, what kind of loads are there, priority loads, non-priority loads, and accordingly the SAFI index will be there. And similarly, SADI index.
Okay, thank you so much, Professor Mohanta, and I would like to give a warm vote of thanks from our complete organizing team and on behalf of our participants also. And your presentation has been enjoyed a lot by our participants, and they are even asking to collaborate and work with you also. So we will provide them. We will provide your email ID and. Okay, thank you so much. Thank you so much. Have a nice day.
Thank you, sir.
And I sincerely apologize if any mistake is from my presentation.
No. There is no need of.
Now, you are all teachers. Insightful. You are all teachers. Honestly, give feedback so that I can improve. This is one of the reason I like to be in faculty presentation, because
we need to provide a feedback, because our participants are already given you a good feedback, and it is visible in the chat box also.
I give that honest feedback where I can, where I can also improve, because every teacher is a learner. We are all always a learner.
Yeah,
so,
absolutely.
I thank you all very much for kindly sparing your valuable time.
Second speaker, Professor.
I'm ending.
That is waiting for that. Now I would like to close this session. Thank you very much, sir. Thanks.
Thank you all very much.
Thank you.